Hello everyone. So the problem that I'm going to be looking at in this video is kind of summarized by this diagram that I've got at the top left. We have an ellipse with semi-major axis A and semi-minor axis B. I've got a coordinate system, Cartesian coordinate system, aligned with those axes. I also have a unit vector D, so it's a normalized vector which is just defining some particular direction in 2D space. The question we want to answer is, as I've written here, which point on the ellipse is furthest in direction D? In other words, how, if you want to stay on the surface defined by the ellipse, but also maximize the projection of that point onto axis D, where are you going to end up? Now, this is something called the support point of the ellipse. It's kind of an interesting problem just to look at, but it does also have practical applications. In particular, this is something I came across when I was doing some coding and trying to determine whether two shapes in two-dimensional space are overlapping. All right. So anyway, let's get on with solving this. And I'm going to start by pointing out that you can parameterize your ellipse as follows. So your general two-dimensional position vector xy can be written as a cos theta, b sine theta, right? This is a standard parameterization of the ellipse. In terms of theta, you can think of theta as an angle that goes anti-clockwise from the x-axis. But essentially, it's just a parameter, can take any value. Whatever we plug in for theta, we're guaranteed to be on the ellipse if we go with that parameterization. So the thing that we're trying to do is to maximize the dot product of that vector, so a cos theta, b sine theta, onto the direction defined by d. So I'm going to just split d into components and say d subscript x, d subscript y. Again, we're assuming that d has already been normalized, right? And so if we expand that dot product, which is just the component of a general position vector in direction d, you get a dx cos theta plus b dy sine theta. And we're trying to choose the value of theta that makes that as big as possible. So we could differentiate it with respect to theta and see what we get, right? So if we differentiate with respect to theta, cos becomes minus sine. So you get minus a dx sine theta. Sine becomes cos, so you get plus b dy cos theta. And if we're trying to maximize it, we're looking for a turning point basically. So we're going to set that equal to 0. Now, if you look at that equation, you should be able to convince yourself that it's only satisfied if cos theta and sine theta are in the ratio a dx to b dy, right? So this is essentially defining a ratio that the cosine and sine of theta have to be in. So that's one constraint that our theta has to satisfy, but there's another constraint which any theta has to satisfy, which is that the sine squared added to the cosine squared of that value has to give you 1, right? So our second sort of constraint is that sine squared theta plus cos squared theta equals 1. Always has to be satisfied. So this is like a pair of simultaneous equations that we have to solve. The reason I actually wrote this first one in ratio form is because I think that makes it easier to just spot what the solution is. Because if you're trying to make cos and sine come out in that ratio, you can start by just saying, well, let's try cos theta equals a dx and sine theta equals b dy. So that guarantees that the first equation is satisfied, this ratio. Then all we have to do is scale them appropriately so that when we square them and add them, we get 1, right? And so what we could do is divide by the square root of a squared dx squared plus b squared dy squared. Do the same for the sine theta, right? So I'll just copy and paste that over here like this, okay? And then by sort of normalizing by that factor, if you try squaring them and adding them together, you'll find that you do indeed get 1, right? So we've got our values of cos theta and sine theta that we need. And in fact, you don't even have to solve directly for theta because you can take the cos and the sine and plug them back into your original parameterized position, right? So if we call our support point that we're looking for P, let's say, it's going to be, let me again copy that normalizing factor. So you're going to get 1 over our normalizing factor multiplied by a position vector, which is a cos theta and then b sine theta. So we get a squared dx because there's an a over here and then an extra a over here. And similarly, we get b squared dy because there's a b there and an extra b there, so it ends up squared. And there is our support point in direction d, assuming again that d is already normalized. Graphically, we can kind of just spot where that is on the diagram. It'll be in the configuration that I've drawn it, it'll be somewhere over here because then your projection onto that axis is going to be as big as possible. So I could write point P there. Couple of other things that we can say about this. You might notice that I could have put minus signs in front of both the cosine and the sine because then they'd still be in the correct ratio, but they'd still square and add to 1 because putting a minus sign in the front doesn't change what happens when you square it, right? So that would be valid, but then we'd be minimizing the projection instead of maximizing the projection. So that would be the support point in direction minus d, essentially. One little check we can make on our answer is considering the limiting case where the semi-major and semi-minor axes become equal, in which case our ellipse is just a circle, right? And so we could call A and B R in that case. So let's consider what happens if A is equal to B, which in turn is equal to just this value that we're calling R for radius. If you substitute those in, you'll see that because A and B are now the same, the A's in the normalizing factor cancel out with the A's in the sort of vector, the column vector that I've written there. And this whole thing just simplifies to P is equal to the radius times the direction d, which makes sense because it just says for a circle, if you want to go as far as possible in direction d, you just go in direction d for a distance equal to the radius, which makes sense because it's a symmetrical shape, right? So this is all consistent with what we'd expect in this limiting case of a circle.